We are going to continue from the chi-square test. Maybe you have already heard about it in statistics course. Chi-square test is another test which can test the uniformity of random numbers generated through a random number generation scheme. However, there are some drawbacks of the chi-square test compared to the Kolmogorov-Smirnov test. First of all, you need to have a sufficiently long random number sequence. Okay? And also, the chi-square test loses some of the information over the random number sequence. Therefore, the results of Kolmogorov-Smirnov test are much stronger, reliable, much powerful results than the chi-square test. So why we are learning another test? Chi-square test is actually less complex. So if you have a very long random number sequence, then applying Kolmogorov-Smirnov test is just going to take a very long time for this sample size. But chi-square test is much more practical in these kinds of situations. It basically summarizes the information and produces some small size statistics about the sample itself, and you make a decision about the uniformity based on that statistic. Now, how do we perform the chi-square test? Suppose that you have a sufficiently long random number sequence and you divide the unit interval into n intervals, and these should be equally spaced subintervals. And the proper choice for the number of equally spaced subintervals that would divide the unit interval should be between square root of n and n over 5. For example, if capital N is 50, then for a proper choice is what? 50 divided by 5 is 10, and square root of 50 is a little larger than 7, then this means you either divide the unit interval into 8, 9, or 10 subintervals for a sample size of 50. Okay? Then you use the test statistic. So this is the test statistic. Basically, in order to understand this test statistic, we need to define these two concepts, observed frequencies and expected frequencies. The observed frequency is the number of random numbers that fall in each sub-interval that you have created. So you have created n sub-intervals within the unit interval, and OJ is the observed frequencies of these random numbers in each sub-interval. Of course, the sum of OJ values should be equal to capital N. And AJ is the expected frequencies, the theoretical frequency that you expect, which is easy, capital N divided by N, because we have a theoretical uniform distribution, right? So capital N divided by N. If you have 50 observations and 10 subintervals, then you expect in each subinterval to observe 5 of them, right? So this is the expected observation. By the way, expected frequency can be non-integer value as well. I mean, if you have 40 observations and if you have 6 subintervals, let's just say, then 40 divided by 6 gives you a rational number, and let's just leave it as it is. Do not change it to an integer value. So the observed frequencies are always integers, but the expected frequencies are theoretical values and expectations, so they may not be integers, so be careful. So what you do is, in this formulation, for each subinterval, you calculate the difference between the observed frequency and the expected frequency, and that is just a deviation of the observed frequency from the expected frequency, and you square that deviation, and this squared deviation is divided to the expected frequency in that subinterval, and which is just going to be the same value because all expected frequencies are going to be the same because of these equally spaced intervals. And finally, you sum these values up, and the summation of these values will produce you a test statistic, and theoretically the sum of the squared deviations divided by the expected frequency are called a chi-square random variable. And this chi-square random variable is going to follow a chi-square distribution with degrees of freedom n minus 1. N is the number of subintervals, and you are decreasing the number of subintervals by 1, and you are determining your degrees of freedom here. Now, after determining your test statistic according to this formulation, you need to check the percentage points of the chi-square distribution for degrees of freedom n minus 1. Remember, n is the number of subintervals that you have chosen. And when your critical value is less than the test statistic, then this means the test statistic produces a large deviation in at least one of the intervals here. This means the observed frequencies and the expected frequencies are not really matching with each other. There is a significant difference in some of the subintervals. Therefore, you say that the sample does not imitate the uniformity property, and you are basically statistically proving that the sample is non-uniform. However, if the test statistic is less than or equal to the critical value of this chi-square distribution with degrees of freedom n minus 1, in that case, you say that there is not enough evidence to reject the null hypothesis. There is not enough evidence to reject the fact that it is uniformly distributed. This means it is possible that the random number sample may fairly come from a standard uniform distribution as well. So this is the percentage points of the chi-square distribution for new degrees of freedom. Now, depending on the number of subintervals, you are going to determine nu as the number of subintervals minus 1. And for the significance level choice, you are going to choose the critical chi-square value from one of the columns. Now, let's practice this. We have a random number sample of size 50 here, and we are going to apply a chi-square test to these random numbers. And the number of subintervals for this question, what I choose is 5. Actually, we should have used the subintervals determined according to these inequalities. However, for this implementation, I do not want to lose so much time, and I want to make things simplified. Incorrectly, I am choosing the number of subintervals as 5, but actually, it's not a good choice for the number of subintervals. So this means I'm going to divide the unit interval into 5 equidistant subintervals. So 0 to 1 over 5, 1 over 5 to 2 over 5, 2 over 5 to 3 over 5, 3 over 5 to 4 over 5, and 4 over 5 to 5 over 5. Now, these are my intervals. I am labeling my intervals with index 1, 2, 3, 4, and 5. And basically, I count how many observations do I have in the first interval. So it says there are 6 observations between 0.0 and 0.2. So let's find them. The first one here, 0.0720. And another one is 0.0684 here. Another one is 0.0553 here. Another one is 0.1033 here. Another one is 0.1185 here, and another one is 0.1324 here. So the observed frequencies in the first interval is 6. However, theoretical expectation is 10, because if you have 50 random numbers uniformly distributed, you expect 10 of them to fall into these equidistant intervals. So we have 5 equidistant intervals, so we are just sharing these 50 observations equally in each of them. As we have said, expected frequencies are theoretical values. They are not supposed to be integer all the time. So you calculate the differences between the observed frequencies and the expected frequencies in each interval, and you square these differences. So you get 16, 1, 36, 4, and 9. So you see there is a significant difference between the observed frequency and the expected frequency in the third interval. And then these squared differences by dividing them to expected frequencies, and that produces a 1.6, 0.1, 3.6, 0.4, and 0.9 here. You sum these values up, and that produces your test statistic in the chi-square test, which is 6.6. Now, what I need to do is I need to compare 6.6 with a critical value that I need to find from my table. So my significance level in this question will be 0.05. And because I have used 5 subintervals, I need to choose degrees of freedom as 4. And for significance level 0.05, I am just going to choose my critical value as 9.49 from chi-square table, as you can see here. Degrees of freedom is 1 minus the number of subintervals, and significance level 0.05, 9.49. Now, So 9.49 is my critical value, and obviously my test statistic is less than that value. So because my test statistic is less than the critical level, which means the differences between the observed and expected frequencies do not produce a significance value. Therefore, they are approximately matching with each other, we can say, and we say that there is not enough evidence to reject the null hypothesis. The sample may as well come from standard uniform distribution. Now, otherwise, if the chi-square test statistic was greater than the critical value, in that case, you say there is enough evidence to reject the null hypothesis, enough statistical evidence to reject that, and this means you have proven the alternative hypothesis again. The sample does not conform to the uniformity property.